It is known that Earth's magnetic field over northern Canada points straight down. The crew of a Boeing 747 aircraft flying at 260 meters per second over northern Canada finds a 0.95 volt potential difference between the wingtips. The wingspan of a Boeing 747 is 65 meters. What is the magnetic field strength there? So in this problem, we have an airplane flying over northern Canada, and we're told that this airplane is flying in a uniform magnetic field. Well, let's do a sketch of our airplane. So this won't be the best airplane, and it certainly doesn't look like a Boeing 747, but it'll be good enough for our example. So here's our airplane. This airplane is flying in a uniform magnetic field, and that's the magnetic field over northern Canada, and it points straight down. So let's illustrate the fact that the magnetic field is uniform and pointing straight down by using a set of x's. And these x's, remember, represents that the magnetic field is pointing straight away from us. Let's also illustrate that this Boeing 747 is moving with a velocity v. And the speed of this aircraft is at 260 meters per second. We're told that the wingspan of this Boeing 747, which I'll call L, is equal to 65 meters. We're also told that there is a potential difference established between the wingtips of this Boeing 747. So I'll call the potential difference at the bottom wing, let's just label that V0, and the potential at the top wing, we'll label it V. And we're told that this potential difference, V minus V0, is equal to 0.95 volts. Using this information, we have to determine the magnitude of the magnetic field through which this Boeing 747 is flying. Now, from what we've discussed previously, we know two things. We know that a conductor moving through a magnetic field has an induced electric field inside of it. Now, that induced electric field is due to the positive and negative charges that separate. So if you were to take a positive charge and wanted to know where that positive charge would end up moving, you could use the right-hand rule. Now, if I use my right-hand rule on this positive charge, my thumb ends up pointing straight up because, remember, we put our fingers in the direction of velocity. Our palm faces the magnetic field, which is pointing away from us. So the magnetic force on that positive charge takes it straight up. So let's go ahead and draw that positive charge at the top, which is at the tip of the left wing. Now, negative charges will experience a magnetic force in the direction opposite to that of positive charges. So negative charges will accumulate at the tip of the right wing. And we know that this establishes an induced electric field between the wingtips. So we know from our previous discussions that this induced electric field has a magnitude of the speed times the magnitude of the magnetic field. And furthermore, it is this induced electric field that allows us to establish a motional EMF, or in other words, a potential difference based on the motion of this conductor in the magnetic field. And we know that motional EMF is equal to the product of the conductor's speed, the magnetic field through which that conductor is moving, and the length of the conductor, at least the length that is perpendicular to the direction of motion. Well, here we have all the pieces of information we need. We know the potential difference. We know the wingspan, that's the length. We know the speed in which this airplane is moving. We need to find the magnitude of the magnetic field, and we could get it directly by dividing the potential difference by the product of the airplane's speed and its wingspan. So this means that the magnetic field through which the 747 is flying is equal to 0.95 volts divided by 260 meters per second times 65 meters. Let's do a quick unit check before we plug this into our calculator. We're looking for units of the Tesla. And we know that 1 Tesla is equal to 1 Newton per amp meter. So what we have on the right side in our result, we have a volt per meter squared over a second. Now remember, a volt is a joule per coulomb, and this is over a meter squared per second. So we have a joule, and remember, a joule is a Newton meter. So we have a Newton meter over a coulomb meter squared per second. A meter in the numerator cancels with a meter in the denominator. We have a coulomb per second in the denominator, which is an amp. So we end up with 1 Tesla being equal to 1 Newton per amp meter. Okay, so the units for this problem checks. And when I plug this into my calculator, I get that the magnitude of the magnetic field that 747 is flying through in northern Canada is equal to 5.6 times 10 to the minus 5th Teslas.